Lim, who is R&D Associate Staff Member in Transportation Planning and Decision Science Group at Oak Ridge National Laboratory. One of the major projects that Lim is involved in is to build freight data product for the public, or so-called FAF, Freight Analysis Framework. This data set provides a comprehensive picture of nationwide freight movement among major metropolitan areas by all modes of transportation. Lim.
Hello, my name is Hyeonsup Lim. Before I jump into the slides, a little bit of background. So this study, I was a PhD student when I was getting involved in this study. So I was lucky to have opportunity working in Oak Ridge as a PhD student because University of Tennessee that I graduated is very close to Oak Ridge. Is less than 30 minutes away from university. And I was involved in actually freight analysis framework project. So I calculated, I was estimating the ton miles, which is one of the products in the FAF. And to calculate the ton miles, you have to have county level OD distance metrics, and then you estimate the ton miles. And so DOE asked us, because we normally, as a FAF team, we generate the nationwide OD flows for all commodities. So the FAF data product is typically OD flows by commodity and transportation mode. So DOE asked us to actually have the commodity flows for specifically energy commodities like motor gasoline and diesel and things like that. And this project was kind of very small projects that the DOE asked us, and then we actually finished the project, and then I came up with the idea that we can a little bit improve after I finished the project. But by the time that I graduated from the University of Tennessee, actually after I graduated, I joined the Bank of America for 1.5 years. So I didn't have a chance to follow up on this item. So I came back. I really missed the transportation, so I came back to Oak Ridge, and now I'm following up. So this is not current ongoing projects that we are doing. It's just for my perspective, it's just for fun, and it's kind of exploratory study that at least I think, so it doesn't have really cool or fancy visualizations, but at least I think I can give you some idea or different angles of how we can apply visual analytics or image processing in transportation. So this is flow of crude oil and motor gasoline to the gas station that is explained in EIA, Energy Information Administration website. So the crude oil is extracted from the wells and then is transported to refinery, and refinery process the crude oil and produce the petroleum products, and then stored in the refinery storage, and then actually transported to petroleum product terminals. And the scope of work we did is just from the refinery to the petroleum product. Actually, the gasoline is transported to the end users, which is gas stations, but that was out of scope from the study. So typically what we do so the key challenge that DOE asked us was to have this energy commodity flow at the county level. So there are a lot of information at very highly aggregate level, like a state and national level, but how can we disaggregate to the county? And that's actually kind of a lot of demands from the local agencies for other commodity flows as well. So as a FAF team, what we usually do is we have some control total at the very highly aggregate level. In this case, EIA provides the pad-to-pad movements. PAD stands for Petroleum Product Administration Defense Districts. So they divided the U.S. into just 5 regions, West Coast, and then Rocky Mountain, and Midwest, and Gulf Coast, and then East Coast. And they have OD metrics for that level, and they don't have OD level for more detailed level. So, but they do have origin side. They have production at the state level and also consumptions at the state level as well. So what we do is we use this state level production and state level consumptions as a marginal total, and then we apply some modeling to disaggregate to the county for production and the consumption side, and then you have county level origin and county level destination and production and consumption, and you apply kind of gravity model. The actual technique is called iteration proportional fitting, IPF. So that's what we typically do. That's why actually DOE asked us. So I thought that this is really simple job because I already have done for the ton mile calculation. But today what I'm going to talk about from this study is just focus on the destination side, which is estimating the product petroleum consumption at the very detailed geographical level. Actually, we do have petroleum product terminal locations from EIA. So I was thinking that we can actually have very specific location consumption estimate for each petroleum product. So I summarized just key challenges for very high level. So like I said, EIA provides a very highly aggregate level of the data, so like a pad and state. And another challenge is that the input data is both at the very different levels. Some data is at state level and county level, and you have the data from the link volumes, or there's a point information, which is the location of petroleum products. Another challenge is that you do not have actually ground truth. So how can you validate at the county level or each petroleum product terminals when you do not actually know what the actual petroleum product consumption is? I'll talk about that later. And from the EIA data, there's information of a location for each petroleum product, but there's no variable to quantify what's the rough estimate of petroleum product consumptions, or kind of like capacity that we can utilize to estimate the petroleum product consumptions. For refinery, we do have refinery capacity from EIA websites, but not for petroleum product terminals. And the last one is, so it's kind of typical questions for any research that we are doing. So when you have different levels of data, how can you leverage all the information to better estimate the final result? So here's the rough idea of what kind of data that we have. Like I said, for petroleum product consumptions, we have a state level estimate from the EIA website. It's a published data. So the blue one is motor gasoline, and the red one is EIA defines as a distillate fuel oil. It's actually just diesel. And there are other petroleum product elements like ethanol and kerosene. But here I just presented just the 2 parts, which covers more than 70%. And you have a location of each petroleum product terminals, but no variable to quantify the either capacity or the petroleum product consumptions. and you have some network assigned data that gives you the VMT of each link. So how can we leverage all this information to disaggregate from the state level to the county level or the sub-county level? That's a key question. So this is general steps of what I did for this estimation. So first, we do have location information for each petroleum product terminals, but I want to estimate the capacity of each terminal so that I can estimate the coverage of each terminal, that I can apply the VMT later for each coverage of this petroleum product terminal. So the first is to estimate the capacity, and then I get the coverage by applying so-called the Voronoi diagram. I'll talk about that later. And then within that coverage, I calculate just total VMT, and then apply average fuel consumptions, and that gives you the fuel consumption estimate. So for the first step, which is to get the capacity, EIA does not provide any information, but I was able to find a website that has kind of open source for public, but they do have roughly 1,500 petroleum product informations, but roughly 500 they have some capacity informations, but rest of them they don't. So I leverage this information and I apply some web scraping because it's a lot of tedious jobs if you manually extract the information. So I extracted capacity information and also address, and then convert the address to the longitude and latitude. And so now I have the capacity information for these 500 petroleum product terminals, and for the about 70% rest, I do not have the capacity information. So, and then using this 500 and then divide into half and half as a training set and the validation set, and based on this roughly 250 petroleum product terminals, and applied circle detection, and so that I can get the rough estimate of petroleum product capacity for each petroleum product terminals. So I use a circle half transform. I'm not expert at the image processing. This is kind of first time that I apply some image processing, but I want to give you the idea that, I mean, as a transportation engineers, we sometimes need to be really flexible, and you have some ideas and you need to apply something that you didn't know. That it was not too difficult to apply the half transform. There's a Python library, OpenCV, and then it's simply just one line of code to apply the half transform. But the challenge is there are parameters that you can calibrate or adjust to have a better result. Actually, since we have some time, how much time? 10 minutes. Okay, I'll do that later. Okay. So once I get circle detections, and then so this function gives you three outputs: x, y, and radius. And for because petroleum product terminals, the tank, the shape of tank is always a circle cylinder. Because of that geometry, gives you kind of even pressure for all the sides, and so it's always a circle. And because we can estimate the R and go back to the mathematics in high school or middle school, and the volume can be pi multiplied by R squared and H, and this H is also proportional to R. So the R that we can apply to the power of R should be around between the 2 and 3. And I actually applied some optimum value, trying to find the optimal value based on the R square of the petroleum product capacity estimate and the capacity that I got from the energy supply logistic website. So I compared that. I compared the R square depending on this parameter, and then it actually gave the result of around 2.9 was the optimum for this. So that's another check that is it reasonable to apply these things. That gives you some confidence that, okay, this makes sense. And once I get the petroleum product capacity, now I apply the coverage of each petroleum product terminals. So if I do not have capacity information, or I do not apply capacity information, then I can apply unweighted Voronoi diagram. It's just to make a boundary between the multiple points that's find the midpoint of each locations, and then build a boundary of each point. So from the point features, output of this method is to be a polygon. And if you apply, now you have the capacity information, then you can apply some weight on this method. And because some terminals can handle more than the others, so the basic idea is this petroleum products with a larger capacity covers more than the petroleum products with a smaller capacity. So once I get this boundary or polygon, then I apply the clipping to get all the links within this boundary, and then I just calculate the total VMT. And total VMT1, so because we have routed network assignment results from the FAF, one of the products in the FAF is this network assignment results, and then gives you the truck volume, and there's information of VMT for light duty vehicle or the all vehicles from the HPMS. So I just apply the both informations to get light duty vehicle VMT and then truck medium heavy duty truck VMT. And highway statistic VM1 table has the fuel consumptions by these vehicle types, and so I can obtain the average fuel consumption by VMT for trucks and also light duty vehicles. So I multiply that factor to get fuel consumption at the terminal level. So once I get the terminal level consumptions, then I aggregate back to the state level to see how different from the EIA numbers. And at this moment, I can just simply adjust this state level to match or to conform of the numbers from the EIA. So I apply some factors for each petroleum products to match with the EIA numbers. But I actually go back to the process 2, which was the Voronoi diagram. Yep. Oh, yeah. Almost done. Yeah. So if you remember, so I applied some capacity, but this capacity is calibrated based on this beta parameter. So I apply some power to this estimated capacity, because I realized that the Voronoi diagram is very sensitive to this weight, and the output, the optimum beta that I got is around 0.2. So the actually minimum of this weighted value and maximum of weighted value was not so different. So I find the optimum beta, then I apply again, and then finally I adjust based on the EIA numbers to conform with the state level estimate. So I think there are a lot of research questions in details, but I just highlighted kind of common questions that we always have for any research. So what's the better method to estimate this disaggregate level? One example is that, so going back to this so-called detection, I realized that the location information that I got from the address is not really representing the center point of the petroleum product terminals. So once I get some so-called detections, I can actually move to the centroid of these detected circles. Well, I was actually working until the last minute, but I couldn't update in the result in these slides. So I got some improvements on that part. Also, when you apply just so-called detection, the default function does not provide a function to avoid overlapped circles. So I also working on that, but couldn't update that part. Oops. Yeah, another thing is how can we validate the result? It's not just the output results, there are also input as well. How can we trust the numbers from that website or the EIAs? So can we leverage like machine learning or image processing to actually validate the not only just location of the petroleum product terminals? They may say there's a petroleum product tanks, but when I look at the images, some they don't have tanks. So that's another point that we can apply. So I just listed just two examples that we can verify the validity of these locations, and also we can also check the mode access of each petroleum product. Yeah, I think I wasted too much time. Yeah, thank you. Yeah, sure. Yeah, I just calculate the R square within the state level estimate from the not adjusted from the petroleum product level. So I have a petroleum product level estimate. I just aggregate to the state, and I do not adjust anything further. And then I compare with the state level EIA numbers and just calculate the R square. And then I go back to change the beta of this weight on the Voronoi diagram and calculate the R square again. So I keep doing that, just get the beta that gives you the maximum R square. Does it answer? Yeah. 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 Purely. Yeah. But yeah. Mm-hmm. Yeah, like I said, it was relevant to the project that we already finished, and then I was just left as a to-do list as in the future, and then I left Oak Ridge, and then I came back. So I'm just following up. So it could be our future study, possibly, but right now for this presentation, it's just my personal idea, just sharing idea for what you can apply for transportation analysis. Yeah. It's not mature the tool, but from the process 1 to 6 that I explained, that they are all automated. So you can just play with different numbers and different inputs. Yeah. Thank you very much. Thank you.